All right, so we're all okay at this point with noticing what a geometric sequence is and figuring out what value each term in that sequence is, right? This sequence that you're looking at here, if I tell you that a sub n is a sequence, is clearly geometric because it's written in the form of an explicit geometric sequence. We've got our r value here, there's r, and we've got our first term here, and the r is being raised to the n minus 1 power. So if I were to write out the first 10 terms, or the first few terms of the sequence, let's just do a few. The first term would be 2, right? Because if I plug in a 1, I would end up with 2 here. If I plug in a 2, I would end up with an 8. If I plug in a 3, I would end up with a 32, and so on. This would continue, right? So in order to figure out what the formula is to find the value of a geometric series, we're going to have to generalize this, and we're going to say instead of using numbers, let's use letters to represent any possibility for a first term or for r that we could conceive of. So let's say that we have, instead of a of n equaling this sequence, let's say that a of n equals a much more general sequence. All right, much more general, where a obviously represents the first term and r obviously represents the common ratio. But what we're going to do is we're going to add together the first n terms of this sequence. So if I'm going to add all these terms together, I have to know what they are, right? What is the first term of this sequence? Well, if I plug in a 1, 1 minus 1 is 0, r to the 0 is 1, a times 1 is a. So the first term of this sequence is a. What's the second term? If I plug in a 2, 2 minus 1 is 1, r to the first is r, a times r is ar. And this continues. If I plug in a 3, I get ar squared. If I plug in a 4, I get ar to the third. And this goes on and on and on. But when does it stop? Well, it stops whenever n is equal to n, right? And if I plug in an n here, we just have a times r to the n minus 1. So the end of this sequence, or the end of this series rather, ends with a times r to the n minus 1 power. And if I say that I'm going to add up the n terms of this sequence, that's what I mean. I mean start with a and end with the nth term. So those are the values that I would add. So what we're going to do now is we're going to dream up another sequence. Let's modify this sequence just a little bit, and let's see what we would end up with. If I took this whole sequence, this whole thing, and multiplied it all by r, what would I get? So let's dream up a new sequence. This sequence, r times s of n. Okay? So I'm going to add together all these terms as well. Well, what that basically is doing is taking r and distributing it into every single one of these terms. So that's going to leave me with a times r as my first term in this series that I'm adding. I'm going to have a times r squared in my second term, a times r to the third, a times r to the fourth, all the way up until, and I'm going to do this over here to the side in blue. The last thing I'm going to do is I'm going to do r times a times r to the n minus 1 power. And to figure out what that's going to end up being, I'm just going to rearrange this a little bit. A times r to the n minus 1. This is the same thing. And the reason I write it like this is because now I'm very aware of the fact that I'm multiplying two terms that have the same base. And whenever we multiply two terms that have the same base, we just add the exponents. So this really becomes r to the 1 plus n minus 1 power, which ends up just being n. All right, so with a little bit of exponent algebra there, we end up finishing with a times r to the n power. So now we have these two series. We have the series of the first n terms of a of n, and we have the series of the first n terms of a of n multiplied by r. Okay, these are two very important series in this definition that we're about to come up with. So what we're going to do is we're going to take the original series and we're going to subtract this new series from it. Okay, so what's that going to look like if we did this using subtraction just like we do with most things? Well, I have my first series. I have a plus AR plus AR squared. I'm just going to generalize it a little sooner this time. But we know that it continues all the way to when it's being raised to the n minus 1 power. And I'm subtracting from it this second sequence. But something you're going to notice is very unique about this second sequence. Notice that once I multiplied all these terms by r, we pretty much got the same exact values in a lot of spots, right? This term shows up in that original series. And so does this term. That's here too. And this term. And in fact, every term shows up in this series except for this last term. That term will not show up in the original series. And we're going to notice that this term here doesn't show up in the bottom series. So what I'm going to do here to make this subtraction a little easier on myself is I'm going to shift this one place over to the right and shift this one place over to the right and shift this one place over to the right and keep doing that until I push this term off the edge. It's going to make my subtraction much easier. So I'm subtracting this whole series, and I'm going to put the AR here and the AR squared here, and it's just going to, everything gets shifted over to the right, the AR to the n minus 1 power plus A times R to the n. So in case you are at all confused, this series here is the number I'm starting with. And this series here is what I'm subtracting from that original series. So I'm doing the series of the first n terms minus r times the series of the first n terms. So this is this piece. Now I'm going to subtract, and you're going to see something interesting happen here. When I subtract these terms, it's kind of like when I do regular subtraction, right? Or if I'm subtracting any two functions, I don't have any like terms here that I can cancel. So a minus 0 is just a. But when I do AR minus AR, those cancel. And I do AR squared minus AR squared, those cancel. And all of this cancels, and this cancels. But what doesn't cancel is the 0 minus A times R to the n. So we end up with A minus A times R to the n power. So I had the series of the first n terms minus R times the series of the first n terms. And that ended up equaling A times, or A minus, A times R to the n power. That whole thing canceled away, and I ended up with just those two things. Okay, so how is that helpful to us? Well, I see some like terms in here that I could factor out an A and end up with 1 minus R to the n power, right? And on the other side, I could factor out my series of the first n terms. All right, so if I want to figure out a general case for how to find the first n terms of any sequence, I just have to get this term alone in this little algebraic equation here. In order to do that, I'm just going to divide by 1 minus r. So I end up with the series of the first n terms equals A times 1 minus r to the n over 1 minus r. And that is a proof of the formula for determining the first n terms of any geometric sequence. This formula is a formula that you will see pretty frequently. Sometimes you see it written as A1 minus A1 r to the n over 1 minus r. These are the same thing. This is just after the A has been distributed, and if we're calling it A sub 1, meaning the first term. But we've been referring to the first term the whole way through here. So this formula shows you where, or this proof rather, shows you where this formula comes from. You don't have to know this in an Algebra 2 class, but it's never a bad thing to know the origin of a formula that you're going to use often.